Hey, good morning, everybody. Again, we continue our exercises for Physics 108B, end of the chapter problems. And in this video, I'm going to cover some of the problems, and in a few videos after this, I'm going to cover a couple of problems from chapter 28, which involves the concept of special relativity. The first problem that we have, a very simple one, and is number 2, and essentially asks you to calculate the gamma factor. So the gamma factor is essentially the connects the rest frame velocity, the rest frame length, the rest frame time with the actual observed length or time by an observer compared to another one that is moving at a certain speed, related to the speed of light, of course. So this exercise essentially asks you to calculate gamma for two velocities, which are conveniently already expressed as a function of the speed of light. So one velocity is 0.1 c, which is 10% of the speed of light, and the second velocity is 0.9 c, which is 90% of the speed of light. Okay? By definition, gamma is 1 minus this velocity square over c square, and that number for the first velocity is 1.00504. So it's very important, because we're dealing with such a small velocity in this case, they will really carry on many digits, significant digits in these expressions. Okay, if you would have rounded to the first or second digit, you would not notice the difference with the normal velocity, right? Now, the second velocity was 90% of the speed of light, and in this case, when you plug in the numbers, you get a gamma which is 2.294. Okay, so time dilates almost 3 times. In this case, 2 times and 2.3 times, while in this case it will almost remain the same. And vice versa, the length will shrink with a factor of 2.5, 2.3, and it will almost remain the same in the first case. Okay. The second problem is number 3. I have it here on the right board, and I'm going to read it to you. Particles called pi meson are produced by accelerator beams. So these are subatomic particles that, when we have accelerators that make smashing particles together, they are produced. If these particles traveled at 2.7 10 to the 8 meter per second, okay, so close to the speed of light, and live 2.6 10 to the 8 second when are at rest relative to an observer, how long do they live as viewed in a laboratory? So that's why I wrote delta T naught. That's the time of life of these mesons at rest. Okay. Now, of course, they are moving at this speed, so this time, as seen by an observer, looks different. How different? Well, the delta T, the time measured by an observer, is going to be gamma delta T naught. Gamma is 1 minus v squared over c squared, and here I put a minus 1.5, okay? Or you can put 1 over that in the square root, delta T naught. And so when you calculate what this fraction, this factor is, the gamma factor, you get 2.294 times delta T, which is the rest frame life of these pi mesons. So it's 2.6 10 to the 8. The final result is 5.96 10 to the 8 seconds. So we observe them as living longer than they actually do, because they move very close to the speed of light. In a similar fashion, I'm going to jump off to problem number 13, which involves the length contraction. So the text of the problem is the following. How fast would a 6-meter long sports car have to be going past you, you're at rest and they're moving fast, in order for it to appear only 5.5 meter long? So in this situation, we have the rest frame length, which is 6 meter. We have the observed length, 5.5 meter, okay? And so we know that the observed length is contracted of a factor of gamma. So the observed length is L naught over gamma. And so gamma is L naught over L, which is 1.0909. So now we plug in the definition of gamma, 1 over v squared over c all together to the minus 1.5. And that factor has to be this 1.0909. Here you have to manipulate this equation a little bit. And at the end, you're going to get the velocity of the sports car should be 0.4 the speed of light. Okay, so 40% the speed of light.